In this video, we are going to focus on the so-called Wittig reaction of aldehydes and ketones. This is going to be another tool in our kit for creating new carbon-carbon bonds, which, as we've discussed before, it can be pretty challenging to create new carbon-carbon bonds, but extremely valuable to do so because that's how we build complex molecules that are practically useful as things like drug molecules out of relatively simple building blocks. So let's take a closer look at the Wittig reaction. We're going to start with a general reaction, and then we will go through the mechanism for a specific example to understand how the reaction is taking place. So the general reaction is that we're going to start with an aldehyde or ketone. So I'm going to go ahead and fill in my R and R prime groups here. And I'm just going to label this that this has to be an aldehyde or ketone. And so that means that R and R prime are going to be equal to alkyl groups and or hydrogen atoms. What we will react with is a molecule referred to as a phosphorus ylide. So we're going to react with a phosphorus ylide, which specifically the general phosphorus ylide that's used for the Wittig reaction, we refer to as a Wittig reagent. And what is true of the Wittig reagent is that it will have, this is one of the more unusual structures we've looked at this semester, it will have a phosphorus directly bonded to 3 phenyl groups, phenols being aromatic rings, 6-membered rings with alternating single bond, double bond. So the pH there indicates an aromatic branch coming off. And the squiggly line represents what that aromatic ring is connected to. So here we have 3 aromatic rings directly bonded to that phosphorus. And then we will connect that via a bond here to a carbon atom. That carbon has 2 groups, which we'll call A and B, directly bonded to it. And this is one of the 2 resonance structures of the Wittig reagent that I'm showing you here, where the carbon will have a negative charge and a lone pair of electrons, and the phosphorus will have a positive charge. And we refer to this, in addition to referring to it as a Wittig reagent, we can refer to it also as a phosphorus ylide, Y-L-I-D-E, where that ylide term refers to a neutral molecule that has oppositely charged atoms directly bonded to each other. So in this particular resonance structure, we qualify as an ylide here because we have oppositely charged atoms, phosphorus with a positive charge, carbon with a negative charge, that are directly bonded to one another here. There is a second resonance structure of this particular molecule that we could draw, and I will just make you aware of here by showing it, because you may sometimes run into problems where rather than the Wittig reagent being drawn out as the ylide form that we see up top there, you could also see it drawn out as this other resonance structure. Both are going to behave the same in the chemical reaction, so it doesn't matter which of these 2 resonance forms you see drawn out. They are both going to behave the same way in the reaction, and you can convert between the 2 by taking the lone pair electrons from the carbon, bring those down to make a carbon-phosphorus double bond, and alternatively, you can go back in the other direction by bringing the pi electrons over here onto the carbon. This works out like so because phosphorus is one of those unusual atoms that can readily exceed a complete octet, and so this phosphorus has 4 bonds in it to start with. In this resonance structure, you'll notice has 5. That's not an error. That is one of the characteristics of phosphorus, is that it can go over the octet rule, unlike most of the atoms that we focus on here in the organic chemistry class. So another point that I should bring to light when we are talking about the phosphorus ylide structure is the identity of A and B here. I didn't refer to those specifically as R groups for a reason, and that reason is that A and B are very flexible in structure, meaning that they don't have to be alkyl groups or hydrogens. They can be a variety of different groups, such as nitro groups, ester groups. A huge laundry list of things are possible there. So A and B have some flexibility in their identity. So we're not constrained here to a specific small set of groups here, like alkyl groups or hydrogens. Instead, what can be represented by A and B is pretty broad. And at this point, you can really think of a huge variety of the different functional groups that we have talked about so far this semester being possibilities as what can be there as A and B. So when you're looking at a phosphorus ylide, what you're really looking for is this carbon-phosphorus bond, single bond with our charges, or a double bond here in the resonance structure of that down here. So recognize the phosphorus ylide. A and B can be really, at this point, whatever you want it to be. So in this reaction, what's going to happen is that during the course of the reaction, the carbonyl group, the oxygen here specifically, is going to be replaced with the carbon and the A and B groups that is directly bonded to. So we're going to essentially swap out the carbonyl group with the carbon here replacing that oxygen atom. So the oxygen is going to be replaced with the carbon from the phosphorus ylide and whatever A and B groups that carbon is directly bonded to. So let's go ahead and draw out that particular product. And then we will go through the mechanism so that this isn't such a wild mystery about how this actually occurs. So let's go ahead and draw R and R prime. Those were directly connected to our carbonyl carbon initially. So just for reference, I'm going to highlight this in yellow. I'm going to highlight it in yellow over here as well. And then what was our carbonyl group, which is highlighted in green in our aldehyde or ketone starting material, that is where we are going to get our carbon-carbon double bond forming to the carbon from the phosphorus ylide. So our carbon from the phosphorus ylide, that's this carbon right here, corresponds to the one we plug in here on the end of our double bond there. And then the A and B groups that it was directly bonded to, going to tag along as well. So we plug in A and we plug in B. And now we have that entire carbon and the A and B groups from the phosphorus ylide linked via a carbon-carbon double bond over to what was originally our aldehyde or ketone group. So you can use this general information as a template for allowing you to predict the product of a reaction of an aldehyde or ketone with a Wittig reagent. We refer to this as, overall, we would describe this as our Wittig reaction. So this is our general generic Wittig reaction. And now what we will do is we're going to take a look at the mechanism for how in the world this happens. How in the world do we go about replacing the carbonyl group with the carbon and whatever two groups A and B it is bonded to here from the phosphorus ylide. So let's take a look at the mechanism, and we're going to see that the mechanism for this reaction has some similarities to the nucleophilic acyl substitution reactions, or nucleophilic acyl addition reactions rather, that we have been looking at throughout the chapter so far. Specifically, the first couple of steps of this mechanism are going to correspond to that general theme of nucleophilic acyl addition. So let's do an example problem here with a specific molecule that we will use as our starting structure. So I'm going to go ahead and start here with our ketone. I'm going to react it with our phosphorus ylide. So I have our phosphorus bonded to those three aromatic rings, the phenyl groups, PHENYL, not OL. There is no hydroxy group there, so it's not a phenol, it's a phenyl, YL. So going ahead and filling this in, we have our carbon of our phosphorus ylide, and then our A and B groups here are what I am going to fill in next. And those A and B groups, we can make whatever we want. And so I am going to go ahead and just to illustrate the different possibilities here, I'm going to put a nitro group on one, and I'm going to put a carbon-containing group on the other, alkyl group, something like that, just to illustrate the flexibility of this reaction. So now what we will do here, now that we have our phosphorus ylide reacting with our aldehyde or ketone, that is the magic mixture for allowing us to go through this Wittig reaction mechanism. So in the Wittig reaction, if we are working from this resonance structure here, we notice that the carbon is a nucleophile. It has that lone pair of electrons on it, and that's going to make that carbon suitable for attack on the positively polarized carbonyl carbon, like so. So this step is completely analogous to when we were working with the nucleophilic acyl addition reactions under basic conditions, in that there's no acid present. The nucleophile, the carbon here, is acting as a carb anion, so it's basic, it's anionic, it's going to come in, attack this positively polarized carbonyl carbon as the pi electrons go up onto the oxygen. So now let's go ahead with the next part of this. So I'm redrawing what originated from our ketone in black here. So this was everything that originated from our ketone up here that I'm highlighting in black. All of that I've copied down here like so. And now we form the new carbon-carbon bond to our carbon right there. I'm showing that new bond that we're using our electron pushing arrow for here in red. And that is directly bonded to the carbon of the phosphorus ylide. That carbon of the phosphorus ylide is directly bonded to 4 groups, so I'm going to plug those in here, here, and here. And in our phosphorus ylide, the 4 groups that we are directly bonded to are our phosphorus, positive charge there, 3 of those aromatic rings, like so, nitro group, NO2, and our carbon chain here, our alkyl group, like so. So this all corresponds now, I'll highlight here for you, what we have shown in yellow up top here is what I've redrawn in yellow down below. So we had our carbon that had formed a bond to the carbonyl group of the ketone. That carbon's bonded to a phosphorus, which is bonded to 3 phenyl groups, bonded to a nitro group, and bonded to the alkyl group, like so. So this is our intermediate. We aren't to the end yet, of course, because we haven't shown how we are going to ultimately end up replacing the carbonyl group with a carbon-carbon double bond over to our phosphorus ylide. But this is our first intermediate. The first intermediate corresponds to the nucleophilic carbon of the phosphorus ylide attacks the electrophilic carbonyl. So now what's going to happen is where things get a little different than what you are perhaps used to. But we can logically work our way through this based on what we know about reactions. In this particular molecule, we have a negatively charged oxygen, we have a positively charged phosphorus. We mentioned before that phosphorus can exceed the octet rule. And so what's going to happen here is an intramolecular reaction step where the negatively charged oxygen is going to come down and form a covalent bond to the positively charged phosphorus, because we can do that without the phosphorus going over its allowed valence. So oxygen anion comes down, forms a covalent bond to our phosphorus. So let's go ahead and show the product of that particular step. So I'm just going to move this over a little bit here so that I have enough room to show what's happening in that second step of the mechanism. So second step of the mechanism is that we get an intramolecular attack of the oxygen anion on the phosphorus cation. So this is going to create a ring. Intramolecular reactions where we link one atom from the molecule with another will create a ring. And specifically, this is going to be a 4-membered ring because we have our phosphorus atom coming over to the carbon atom here, up to here, onto the oxygen, and then that oxygen is going to become linked to the phosphorus. So in total, there will be 4 atoms. I'm going to arbitrarily number those as 1, 2, 3, and 4. In blue there, 1, 2, 3, 4, to illustrate that those are going to be the 4 atoms of our ring. And so what I'm going to do is I'm just going to plug in those 4 atoms of the ring over here. So oxygen formed a bond to phosphorus. I'm going to put an OP bond in there. We had a bond over to carbon from phosphorus, the bond from that carbon then comes up to the other carbon, which then goes over to the oxygen. And to help you in locating where each of those atoms are, I'm also going to number them. So phosphorus we called 1. The carbon that phosphorus was connected to we named as 2 here. The next carbon we named as 3. And then we called the oxygen number 4. This is not following IUPAC numbering or anything like that. It's numbering to help us in determining what's happening in the reaction, because we need to plug in the branches. And to plug in the branches, we need some guideposts to help us doing that. So at 1, we had a phosphorus that had 3 phenyl groups on it. So I'm going to plug those in 1, 2, 3. Plug those in as pH, 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 like so. At position number 2, that was our carbon atom that corresponds to over here. We had a nitro group, and then that alkyl group branched off of it. So I'm going to plug that in as nitro group, NO2. Alkyl branch coming off, boom, 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 like so. At position number 3, we have our oxygen, which is part of the ring, and we also had 2 of these ethyl groups there, so I need to plug those in as well. So I plug in ethyl group and ethyl group, like so. Those correspond to the groups that we had in gray. So I'm just going to put those in gray to emphasize that those correspond to the groups in gray over here. And now we have this ring. And within this ring, you'll notice there are no formal charges on any of the atoms here. That's a good thing, and that drives the reaction toward favoring this four-membered ring. What ultimately, though, will prevent the four-membered ring from persisting long-term is a couple of things. One, a four-membered ring has a lot of angle strain going on, and so that makes the ring prone to reacting. And the other thing is that the structure here of this four-membered ring with an oxygen, a phosphorus, and these 2 carbons in the ring is relatively unstable. And so what's going to happen is that the ring will collapse. So let's take a look at that ring collapsing. I'm going to zoom out here so that we can get a better look at that. So zooming out, now we're going to go into the last step of this mechanism, which is what I'll refer to as step 3 here, which is that the ring is going to collapse. And when we say the ring collapses, that means it's breaking apart to give our product that has the carbon-carbon double bond in it. So let's show how that happens. There's a very specific way that this is going to happen. The carbon-oxygen bond here is relatively weak, and it's favorable for the electrons from that bond to come over and form a more stable phosphorus-oxygen double bond. So what we do is we take the electrons from the carbon-oxygen bond, push those over here to make an oxygen-phosphorus double bond. As that is happening, what would go on if all we did was that is we would end up creating a carbocation right here at position 3. To avoid having to create a carbocation, which is inherently not the most stable thing in the world, we can break this weak carbon-phosphorus bond and bring those electrons over to here to make a carbon-carbon double bond, giving us the alkene group that we observe in the final product. And so through this set of 2 electron-pushing arrows occurring simultaneously, it allows the reaction to avoid forming any additional cations or anions during the reaction mechanism. We go straight from here to a final product that will have no formal charges. So let's go ahead and write out what that final product will be. And we have to think about the fact that we have broken some bonds apart here. So we are breaking this ring in 2 different places. We're breaking it where I'm showing the red breakage here, because we took those electrons from that bond and we moved them over to make a phosphorus-oxygen double bond. We're also making a second break in the ring right here. And so that second break in the ring, I'm highlighting in pink now with my laser, with my pointer. And so with those 2 breakages, what that means is that we are no longer going to have the bond right here. We're no longer going to have the bond right here. And so in essence, based on these squiggly lines that I've drawn, what we show is that the molecule is broken completely in half. So we end up with 2 products of this reaction. One that corresponds to the left half of the molecule right here, because we'd made a cut here and here of the bond, and another molecule that corresponds to the right half of this coming on down to the product. So now we'll go ahead and draw that out. First things first, I'm going to draw the phosphorus side of the products. So we have our phosphorus directly. So the phosphorus directly bonded to the 3 phenyl groups, rather, PH, PH, PH. And as well, we additionally, in addition to having that phosphorus bonded to the 3 aromatic rings, we also create our alkene. It's okay to put the alkene vertical. You could also rotate it to put it horizontal, but I'm showing it the same way that we did up here, which was it will be vertical, just for ease of drawing. It's going to have 2 ethyl groups directly bonded to it. Those 2 ethyl groups correspond to the ones that were bonded up here at position 3. And then down at position 2, we have a nitro group and our alkyl group bonded. So we'll go ahead and draw that in. Nitro group in O2, alkyl group drawing out that chain like so. And this is our major organic product of interest, is this compound right here. So you will notice that the end game is that we have taken the carbonyl group and we have replaced the oxygen of the carbonyl group with the carbon from the phosphorus ylide and whatever 2 groups that carbon from the phosphorus ylide was bonded to, in this case the nitro group and the alkyl group here. So this is a really valuable way to make new carbon-carbon bonds within molecules, and quite flexible because the identity of the groups that are bonded to the carbon of the phosphorus ylide is very flexible. So this makes this a really useful way to rapidly build up complexity within organic molecules.